Here. Oh, what happened? Ah, there it is. Okay, that's fine. Okay, good morning, guys. Hope you had what was a reasonably quiet night and then some interesting morning. I hope you're all fine. Um, can you hear me? Can you see my screen?
Yes.
Yeah.
Okay, very good. Okay, so we're talking about cosmology. Today actually is going to be a very different lecture than Thursday. So we are doing cosmology. And do some recap. Let me just things here so it'll be easier for me to write down. So last time we spoke about the basic principles of cosmology. And the basic principles of cosmology is based on the Copernican principle, which essentially states that there is nothing special about us. And in mathematical words, this states to the idea that cosmological principle in the modern day version, which state that the cosmological principle, which states that the universe is homogeneous and isotropic on a large scale. Cosmological principle. The universe is homogeneous and isotropic on a large scale. Now, of course, we know this is not true. Homogeneous means that the conditions are the same everywhere. We know that it's not true. Again, the conditions here in my room and the conditions in the center of the sun are definitely not the same. Isotropic means that everywhere we look, it looks the same. If I look to my right and if I look to my left, I don't see the same thing. So obviously on a small scale, this is incorrect. But on very large scales, scales that is larger than clusters of galaxies, then we have reasons to believe that this is true. So bear in mind that what we're deriving is true only in these scales. It's not true on a small scale like the Schwarzschild metric that we've derived and we talked about previously. Then we said that in a mathematical language, stating that the universe is homogeneous and isotropic is equivalent to saying that the universe, that the metric contains a maximal number of killing vector. And this is, in mathematical language, this is called a maximally symmetric space. So this is maximally symmetric space is a space with maximal number of killing vectors. With which in n-dimensional space, this would be n times n plus 1 over 2, which is n for translation plus n times n minus 1 over 2 for rotations. And then most of what we did last time was algebraic properties to derive the formula that is put here, which is true in a maximally symmetric space. And we proved that in a maximally symmetric space, the Riemann tensor can be written as some constant, k, a number value, times multiplication of the matrix G. So R lambda rho sigma nu is k times G nu rho G lambda sigma minus G sigma rho G lambda nu. And that is true only for a maximal symmetric space. And most of what we did last time was proving that formula. Okay, any questions before we start today's lecture? You see, Uri, it would be good if you could open your camera. I much prefer talking to.
I will. Few moments.
Some black, if possible, if technically possible. Okay, so armed with that, we can now finally derive the Robertson-Walker metric. Okay, there is one thing which is observationally, and we know that the universe is homogeneous, or we assume that the universe is homogeneous and isotropic in space, but we know it evolves in time. That is what Hubble told us. So as I mentioned, technically, what we're up to is a space with a maximally symmetric subspace. Okay, so I should write it down. We seek a metric that describes a universe that is homogeneous and isotropic in space, but not in time. So basically the metric, so we're looking for a metric which will be something like R cross sigma, right? R would be the time, which is different than the space, which is separate from the space, and this would be sigma, would be the three manifold, which is homogeneous and isotropic, which is a maximally symmetric subspace. So the metric we have would look something like ds squared is the minus dt squared plus some constant, a square of t, times g. And now since I'm only using the special part, then I'm going to use Latin indices. So it will be ij of x dxi dxj. So t is the time coordinates, and x1, x2, and x3 would be the space coordinates. And gij is a maximally symmetric metric. This would be the time coordinate.
Asaf, why
Yeah.
we didn't write any function before the dt squared?
Because we can always rescale t.
Yes, but in a Schwarzschild metric, for example, there is a function of coordinates, right?
Yes, but
Not the
this is
function of time.
not be a maximally symmetric, right? If it's a maximally symmetric, every function that I could put in, I could absorb into t. It cannot be a function of the coordinates, of the spatial coordinates, like we had in the Schwarzschild metric, because otherwise then I could not write it, I could not make a complete separation between the time and the space. And therefore the space would not be a maximally symmetric.
Okay,
Okay,
so
if I had a function here, what you're asking for is why don't I put here f of some r, theta, and phi, for example, or x1, x2, and x3, right? Because if I would put that here, that means that the time coordinate would evolve differently in different locations of this space. So I could not say, so this will not be, I could not make a complete separation between the time and the space. Or in other words, I could not argue that this space is maximally symmetric. If I'm making a complete separation, that means that the time coordinate evolve in a different way, independent of what happens with the spatial coordinates.
So that means that there is no any time dilation in cosmology. If we
It's a different one.
don't
Let's
put
see.
any
Drive it and
function.
you'll see. The spatial coordinates do evolve in time. There is this a squared of t here, which has a name. This is known as the 8a of t, not a squared. A squared a of t has a name. This is called the scale factor, which is a constant factor. It's only a function of t. I mean, I could reverse that and say, okay, I have some constant of t, right? But it doesn't really matter. It's a scale factor. It's only a function of time, which is multiplying all the spatial coordinates. Basically, that tells us how big the grid evolves. We'll discuss that quite thoroughly in the coming lectures. Now, I should say, maybe also answering your question, there are no cross terms here, right? I didn't say any cross term there are no cross terms of the form dt dxi. And these coordinates where there are no cross terms, they have a name. These are called co-moving coordinates. Coordinates with no cross terms are called co-moving coordinates. And basically, it's the simplest that you can think of, right? These are the coordinates that are, not moving in space. So I said that if we're looking from the Earth, actually, we're not in a co-moving coordinate because the Earth does move through space, because we are rotating around the sun, and the sun itself is rotating around the center of the galaxy. So that's why when we're looking at the cosmic microwave background, we do see a dipole, but this dipole is attributed to our own motion.
I will be glad if you can explain it again, like what is the co-moving coordinates?
We are fixed. Co-moving means that we are moving with the coordinates. In other words, relative to the coordinates, we're not moving at all. So that's the simplest. When I say something is co-moving, that means that it is moving with the other thing.
Okay.
So these are the coordinates, meaning that, we are with the coordinates. Okay. Only in these co-moving coordinates, the universe looks isotropic. If we are not co-moving, so if we are moving relative to the coordinates, then we're losing isotropy, isotropicity, right? Think of it like that, right? If we're not moving at all, when we're looking at the sky, then technically, I mean, all the galaxies are isotropically distributed around us. So if it doesn't matter which direction I'm looking at, I should see the same number of galaxies, the same, not number, but fraction of galaxies, right? Or density of galaxies per unit angle. If I am moving, then it's no longer true because I have now a Lorentz transformation of angles, which you did in one of the first problem sets. So I'm losing isotropicity. Okay, it's the simplest. I mean, there's nothing to get confused here. It's the simplest thing there is.
And in such metric, we don't have only dt dxi cross terms, or also dxj dxi for different time j.
Let's see that, right? Now we're going to make use of what we derived last time. So hold on a second. So now we had this equation which we derived last time. So I'm going to write it, but now it's 3. I'm going to put the 3 to remind us all that this is only true for the spatial part. So I'm going to write R, use now R, I, J, K, L. I'll put the 3 here to remind us that, which is some constant, okay? G, I, K, G, J, L minus G, I, L, G, J, K. Which is true for maximally symmetric spaces. That's what we worked out in the last lecture. And then the Ricci tensor. Now in 3D, of course. So R, J, L, 3 we obtain by contraction. So if I contract J and L, here I'll just discuss an N, right? And I'm contracting I and K, right? To get JL, I contract I and K. So I'm contracting here, I'll get an N. I'm contracting here by multiplying G, I, K. So I get a delta, so I get a 1. So overall, I'll get N minus 1, K, G, J, L. And since this is 3 dimensions, and minus 1 is 2, then this is 2K, G, J, L. Now, we said that the space is maximally symmetric. If it's maximally symmetric, it obviously has to be spherically symmetric, right? That's part of the symmetry. So we can actually make use of the derivation of the Schwarzschild metric, which we did last time, because this is true for spherically symmetric. We can write down, so for a maximally symmetric space, symmetric is also spherically symmetric. From here, we know that it has to obey, I'll call it not the S squared, but the sigma squared, because it's only 3D, and G, I, J, and dxi, dxj, which can be put in the form e to the power 2 beta of r, dr squared plus r squared d theta squared plus sine squared theta d phi squared. And the derivative is identical to the derivative that we did when we derived the Schwarzschild metric. So I don't need to have anything new here. It's exactly the same what I did. Then we can repeat the same calculation of the Ricci tensor. Now we basically copy paste the derivation, the part of the derivation, right? Derivation of the Schwarzschild metric. And we end up that R11, again, 3, is 2 over R D1 beta. R22 is e to the minus 2 beta. R D1 beta minus 1 plus 1. R33 is e to the minus 2 beta. R D1 beta minus 1 plus 1, and all that multiplied by sine squared theta. No, I did not make anything. I just said, okay, for a maximally symmetric space, it's also spherically symmetric. If it's a spherically symmetric, I can write down the metric in that form here. And if I write down this metric, I just go and calculate what is the component, what is the affine connection, and what are the components of the Riemann tensor, and then what are the components of the Ricci tensor. Exactly what we did in the Schwarzschild. I'm repeating one-to-one, except that I don't need to have the alpha now. That was in there before. So the calculation basically, so that's why I can skip all these steps, because basically we did all these steps. But now we know that in a maximally symmetric space, the Ricci tensor has to look like that. So we can now plug it in. So we plug it in. We get that R11, which is 2 over R d1 beta, is equal to 2K G11. Right? What is G11? What is G11?
Just, R squared.
What? What is G11?
R squared? No.
No. What is G11? R is the coordinate. What is the metric? Component?
Exponent of 2 beta.
Exponent of 2 beta. Right? This is G11. Yeah? So this is 2K e to the power 2 beta of R. And R22
R squared.
Sorry?
R squared.
Yeah. So this is e to the minus 2 beta R d1 beta minus 1 plus 1 is 2K R squared. That's pretty straightforward. You can simply eliminate d1 beta from these two equations. Just plug it in here. What we get is that beta is equal minus 1/2 ln of 1 minus K R squared. Let's plug it in. That's what you're going to get. And that's basically all we need. So we just plug that into the metric here. You get the total metric. Now I'll write it in full. ds squared is minus dt squared plus a squared of t dr squared divided by 1 minus k r squared plus r squared d theta squared plus sine squared theta d phi squared. This has a name. This is the known Robertson-Walker metric. Famous, I don't know. Now, have in mind what we did not do yet. We did not make any attempt of solving Einstein's equation, right? We just use the conditions of a maximally symmetric space, out of which we said it's also a spherically symmetric space. And we got that. Now, we see that this metric has two unknowns, basically, right? One is the scale factor, A of t, So to get A of t, we actually need to solve Einstein's equation, which we will do shortly. And there is also this constant k, which we say we came out of the math, can get any value. Now we don't know what is this value, but pay some attention because we can always, so to get A of t, the scale factor, we will determine after solving Einstein's equation. What about k, the constant k? We can always renormalize. We redefine. So if I redefine, remember k is a constant, I don't know what the value of k is. It can take any value. Right? Nothing in the math told me what the value of k should be, only it's a constant. It's a fixed number. So, but I can renormalize it. If I transform k into k over absolute value of k, and then r into square root of k times r. And then also redefine the scale factor. This way will also kind of answer your question or partially answer your question into a over square root of k. Then what do we get?
K vanishes, just you absorb it in A squared.
K does not vanish. But then I don't care about the exact value of k. K is normalized. Right? K is normalized. So if k is go to k over square root of over absolute value of k, r goes to r times square root. So that means that this part here give me the same result. I still have the dr square here and the r square here, but then I can normalize them by the a square here. Right? Normalize that, then the Robertson-Walker metric is invariant. It's not changed. That means that the only relevant values k that we have are what?
Sine.
Sorry?
It's sine.
Well, it's simpler than sine. Simply plus 1, minus 1, or 0. So we only have three cases of interest. Right? This is k minus 1, k equal to 0, k equal plus 1. Any other value I can normalize to the value. Now they have a name. If a k is equal to minus 1, that means that the space, remember, it's a maximally symmetric space. It has a constant negative curvature. Constant negative curvature space, which we call open. Equal to 0 means no curvature. Then we say that the space is flat. K equal to plus 1 is a positive curvature space. Which we called closed. Now, actually, when you look at it, it's much simpler than you think. We worked very hard to get results which are, in fact, nearly trivial. Let me write it again so that you can see it, right? So if I write down ds squared, I write down again the Robertson-Walker metric. ds squared is a minus dt squared plus a squared of t. And you know what? Forget about the full metric. Let's just look at the spatial part. D sigma squared is dr squared over 1 minus kr squared plus r squared d theta squared plus theta and sine squared theta d phi squared. If k is equal to 0, what is this metric equal to?
Minkowski metric.
Even simpler than that. There is no Minkowski. Well, it is Minkowski, right? But I omitted the time. So it's even not even Minkowski, right? It's a simple Euclidean space, right? So we end up with a dr squared plus r squared d omega squared. Which is just a flat space written in spherical coordinates. Dx squared plus dy squared plus dz squared. This is a simply flat Euclidean space. We worked very hard to get to something which is sort of obvious. Now we have, since we worked hard, we have the other options. If we have k equal to +1. Okay, now what do we have now? Now we write r is equal, so changing variables, I'll write down r equal to sine of chi. And then I have dr divided by 1, k is equal to 1. So dr squared, 1 minus r squared, right? It's simply d chi squared. Then I get the sigma squared is d chi squared plus sine squared chi d omega squared. What metric is that? You don't see it right away? This is, of course, 3 dimensions, right? But if it was a 2 dimension,
Kind of polar coordinates, no?
or what?
Polar coordinates?
What coordinates? I'm
No?
sorry.
Polar.
Polar
This is
or what?
like an open ball.
Exactly. This is exactly the metric that you get on the surface of a sphere. You had that in your homework, right? For a 2-dimensional surface of a sphere. That's the
Yes.
metric you get. Now it's the same thing, only for 3 dimensions, of course.
Yes.
So this is really a 3 sphere. So think of it like, the surface, like I don't have a way of visualizing it. You can easily visualize the metric describing the surface of a ball, like the surface of Earth. But this is, of course, a 2-dimensional surface. So here it's the metric describing the surface of a 3-dimensional sphere. So there's no simple way of visualizing that, but conceptually it's exactly the same thing.
Is it means that the universe is periodic? like, כאילו, זה מה שהיקום מחזורי?
In a
אם
way,
אני הולך לכך.
yes, you're getting into an interesting question, right? If indeed this is the metric of the universe, right? Remember, I think we discussed that in the very first lecture. right? And let's say that I have a telescope, right? And I'm looking at the light ray, right? That goes in one direction. And I'm looking at the telescope. And let's say telescopes are evolving, so I can gradually look further and further and further away. What will I see?
Myself.
Of my head. That's what it means, right? That the light ray would. Now, it's not exactly because the universe also evolves in time, right? But from the spatial part, yes, that's exactly what it means. That if the universe was not evolving in time, that means if I would go, let's say I'm an astronaut, and I'm very sophisticated, far, far in the future, somebody could travel at whatever speed I want, right? I can go in one direction, I'll keep on going, I'll end up going back home. The same as 500 years ago, Magellan went west and eventually went back. Well, he died on the way, but some of his sailors did. It's exactly the same thing. Cool, isn't it? Which is, again, what you'd expect from a maximally symmetric space. It is. Now, this space has a name. So this is a three sphere, I said. So the space has a name. Such a space has a name. This is called the de Sitter space. This space is called the Sitter space. It should be we still have one last final option, which is k is equal to -1. And then in that case, again, we'll change variable rather than r, which is sine phi. You wouldn't be sine psi. You wouldn't be surprised that what I'm going to do is write down r as sine hyperbolicus of some other function. Let's call it psi. And changing the variables, we got that the sigma squared is the psi squared plus sine hyperbolicus squared of psi d omega squared. What metric does that describe?
Paraboloid.
No, not really. Right? First, it's a maximally symmetric space, right? It's a maximally symmetric space with a negative curvature, right? So it's like the saddle that we have, but in every point. So it's very difficult to imagine that. And this is a three-dimensional space. Is a 3D space of constant negative curvature.
Why the inside the surface of a sphere is not a solution?
I'm not sure I understand what you mean by the inside surface of a sphere.
Like if you have sphere, so not the outside part, like
There is no inside and outside here.
בסוף אתה מחפש פתרון שנותן לך עקמומיות שלילית וגם מרחב מושלם.
We discussed that. You have to think a little bit about that. Use your imagination. Negative curvature means that the things curve away from you in different directions in the opposite way. So it will look more like a saddle. It'll look something like that. I don't know how to draw that properly. It will go something like that. But here it will go the opposite. I don't have a simple way of visualizing that. You may want to, I don't know, Google it or something, maybe to give you some intuition. The idea is that you stand here and then it curves in one way, in one direction like that, and in the opposite direction it will go exactly the opposite. I'm not sure that they have a better way of phrasing it, of visualizing it. I mean, think from a mathematical point of view, you know, you can write down the equation, but intuitively, again, I don't have a very good way, definitely not in 3D, to visualize such a space. I mean, anyway, this is the mathematical description, so this is the correct one. Obviously, such a space, as opposed to a ball, right, that is closed, right? This such a space extends forever. Right? There is no. I see there is a chat here. Okay.
I just sent the picture.
The picture, okay.
With different curvatures.
It can be. You go online and you'll find. Try to do whatever visualization of negative curvature spaces. So this such a space extends forever, right? Such a space extends forever. Again, there could be more complicated spaces. There is no point in talking about them right now in this course. That goes to a higher level, which is more mathematics than physics. And this space has a name. This is called anti-de Sitter space. Okay. So we end up, after working very hard, a few hours, getting that there are only really 3 independent solutions of the metric with a maximally symmetric spatial part. One is the flat, one is a positive curvature, one is a negative curvature. This at de Sitter and under-de Sitter. In a way, we could envision that earlier, but now we have the full mathematical proof of that's what it is. Okay. Now have in mind that what we did so far did not even, we used just, symmetric arguments and the math associated with the symmetric arguments, with scaling vectors, and with the curvature tensor. We did not make yet any attempt of solving Einstein's equation. Okay. Okay. Questions? No, then let's move on. So what we're going to do now is solve Einstein's equation. And as I mentioned already, solution to Einstein's equation will give us the evolution of the scale factor A of t, which is what we care about. And the name is called Friedman equations. So,
Saf, can I ask you a question?
Yes.
Can we theoretically predict or derive the true value of constant k for our universe, or if
No.
we can divide it, I mean, get it only from observations?
No, we're going to discuss observations. We'll see what observations can tell us. The answer is no. Because, again, because of this scaling. Because remember that the R and the T, these are arbitrarily chosen. I mean, you can decide to measure distance in centimeters, in meters, in kilometers, in inches, in whatever value you want, right? This is your choice. And remember that we spoke at the beginning of this course that one of the basic principles is that the physics doesn't know and doesn't care about the way we want to measure it. So
Yes.
the answer is really no. We can always absorb that, and the same can be said for the time. I mean, we choose to work in seconds or hours or days or years or whatever you want. But this is our personal choice. I mean, some other civilization that lives in some other galaxy would make a completely different choice. And nobody could say that we're doing any better than them or vice versa.
Okay.
Okay, so the answer is no. It's all absorbed. Okay, so Friedman equations, as I said, we now take the Robertson-Walker metric and use it in Einstein's equation. Okay, so now again, we don't really have much choice, but we have to dirt our hands. So I've dirt my hands. So I'm going to write down A dot is dA over dt. And okay, so just do it. So the Christoffel symbols. Again, you can find it today. Of course, you can do it yourself. You can ask today your computer to do it for you. Or you can simply look at textbook. Any standard textbook will have that. A dot over 1 minus k r squared is gamma 0, 1, 1. Gamma 0, 2, 2 is a dot r squared. Gamma 0, 3, 3 is a dot r squared sine squared theta. Then we have gamma 1, 0, 1 is gamma 1, 1, 0 is gamma 2, 0, 2 is gamma 2, 2, 0 is gamma 3, 3, 0 is gamma 3, 0, 3. And this is A dot over A. Then we have gamma 1, 1, 1 is KR over 1 minus KR squared. Gamma 1, 2, 2 is minus R, 1 minus KR squared. Gamma 1, 3, 3 is a minus R, 1 minus KR squared sine squared theta. Gamma 2, 1, 2 is gamma 2, 2, 1 is gamma 3, 1, 3 is a gamma 3, 3, 1 is 1 over R. Gamma 2, 3, 3 is minus sine theta cosine theta. Gamma 3, 2, 3 is a gamma 3, 3, 2 is cotangent theta. Okay, then you plug this in, get the Riemann tensor, contract and get the Ricci tensor. And then the Ricci tensor components, we get that R0, 0 is a minus 3 A dot dot over A. Second time derivative of A. R1, 1 is A dot dot plus 2 A dot squared plus 2K over 1 minus KR squared. R22 is R squared. A dot dot plus 2A dot squared plus 2K. And R33 is R squared. a dot dot plus 2a dot squared plus 2k times sine squared theta. And finally, the Ricci scalar all is 6 over a squared a dot dot plus a dot squared plus k. Okay. Your options, the best option, of course, for you is to derive all that. The second option is to look at the textbooks, and the third option is simply to trust me, which is the last thing I want you to do. But this is what you get. Of course, we need to put it into Einstein's equation, but now we have to be careful, right? When we wrote down the Schwarzschild metric and we plugged it into, when we find the Schwarzschild solution, right, into Einstein's equation, then we assume that the solution is solution to Einstein's equation in vacuum. So on the right-hand side, we said 0, right? But we cannot say that the universe is empty. Right? It's not empty. It contains various things. So we have to assume that the universe contains something, which is a matter and energy, essentially. So the universe is not empty, but contain matter and energy. So how do we describe the universe?
By the stress energy tensor?
Exactly. You see, now everything comes together. I did not teach you for that for nothing. So we have to use the stress energy tensor. And what we can assume, is that the universe is made of perfect fluid. Right? So we use the stress energy tensor. For a perfect fluid. Which remind you, this is a fluid that is isotropic in the rest frame. So that's basically, the rest frame is the co-moving frame, right? Which isotropic in its rest frame, namely the co-moving frame. In our case. Then the energy momentum tensor, I'm just reminding that you, P mu nu, we show that it is equal to P plus rho, U mu plus P mu. What is P?
The pressure,
Yes, and what is rho?
the energy density.
Right.
Mhm.
U mu.
The velocities of particles in the fluid.
Right. This is the form velocity of the fluid. in the fluid rest frame, which is the comoving frame, what is mu mu? What is an upper index? Easily.
It's just gamma and
Fluid frame.
1 and all of
One.
ours 0.
1, and the other components?
0.
0. It's clear to everybody? This point in your career, it should be clear to everybody. It's rest, right? So it's just not moving. It has to be moving in time. Word line of okay. So the energy momentum tensor is going to be a rho 0, 0, 0, 0, 0, 0. Here I'm going to have the Gij. So we can raise one index.
Can I ask a question?
Yeah.
Why are you using only Gij and not a squared times Gij?
A is inside G.
Okay.
The metric. Right. A is part of the, I wrote down the metric, right? The Robertson-Walker metric is written down here, right? A is already inside the metric. Okay. G00 is, of course, a -1. Everything else is a squared times whatever there is there.
Okay.
Okay. Now I can raise one index. If I raise one index, T mu nu, that's pretty easy, right? I just multiply this by inverse of G. I'm just going to get a diagonal of minus rho P, P, P. And the trace, T, it's just T mu mu. It's just a minus rho plus 3P. Now we can use that in Einstein's equation. So Einstein's equation which we put it in a slightly different form, but it's the same form essentially. R mu nu is 8 pi G T mu nu minus 1/2 G mu nu T. I think we had this exact form when we derived Einstein's equation at a certain point. And now we just need to use the components. So we have the 0, 0 component. R0, 0 we said is -3 A dot dot over A. So -3 A dot dot over A is 8 pi G. T00 is just the rho, right, from here. And plus 1/2, G00 is a -1, so I have a plus 1/2. T, which is a minus rho plus 3P. Or -3A dot dot over A is equal 4 pi G rho plus 3P. Okay. That's one equation we got. That's for the 0, 0 component. Now for the Rij component, Rij, 0j is not interesting, right? So Rij is 8 pi G Gij P, right? That's a Tij. And then I have minus 1/2 Gij minus rho plus 3p. So this is 8 pi G. And here I have 1/2 Gij rho and minus 3/2 plus 1, so it will be minus 1/2 Gij P, which is 4 pi G Gij rho minus P. Now, in principle, there are 9 equations here, right, for I and J, but it's isotropic, so they're all the same equation, essentially, right? So we can simply use the 1, 1, all 9 equations are dependent due to isotropy. And remember that G11 was A squared, so G11, R11, sorry. Oh, sorry, G11, oh, hold on, one second. G11 is A squared divided by 1 minus KR squared. Okay, this is G11. And R11 is that A dot dot plus 2A dot squared plus 2K divided by 1 minus KR squared. So the 1 minus KR squared cancel. And we end up with A dot dot over A plus 2A dot over A squared plus 2K over A squared is equal to 4 pi G rho minus P. Okay? You just plug the 1, 1 term here, use R and use G, and that's what I get. Now we can use the equation here to get rid of the second derivative. And then we can do a little bit of cleaning up, really. So we end up with an A dot dot over A to be equal to minus 4 pi G over 3 rho plus 3P. And then A dot over A squared equal 8 pi G over 3 rho minus K over A squared. It's a trivial algebra to get from these two equations to these two equations. So this is something that you can easily do at home. These two equations have a name. So these are known as the Friedman equations. And overall, the Robertson-Walker metric, which tells us the metric of the universe, plus the Friedman equations, which essentially tell us the evolution of the scale factor, how the scale factor evolved in time. These are known as the Friedman-Robertson-Walker universe. Friedman Robertson, Walker, or FRW, FRW universe. Okay, it's all clear? Questions? Any questions?
Rho and P are time dependence or they're just constant?
No, they're constants.
Oh,
Well, actually, we're going to see that.
okay.
Actually, wait a second. We'll get an answer to that.
Okay.
They are actually they are depending on time.
Mhm.
Rho is the energy density. P is the pressure. Now, before we go into, well, we are going to solve these equations shortly. But even before we're going to solve these equations, we want to have a look at the global properties of the universe. So the first thing we're going to do is to define something which is called the Hubble parameter. Yes, that's after the same Hubble. It's a parameter, it's not a constant, which we call H. So Hubble parameter. H is defined as A dot over A. And that is really a characterization of the rate of expansion of the universe. Now, one important comment here, A by itself is not measurable. We cannot really measure it. So we have to divide A dot over A. This is something which has units of 1 over time. So this is something which we can measure. Right? Again, I was slightly cheating. There is a way of, we'll get to that. Right? But this is something which we can measure. It has basically units of 1 over time. The Hubble parameter. It's called a parameter. It is changing in time. You'll see that. We can also define the deceleration parameter, which we called Q. Deceleration parameter. Q is minus A dot dot over A dot squared, which essentially gives us the rate of change of the rate of expansion. So how do we call Hubble's parameter today? Hubble's parameter is changing in time, obviously. So Hubble's parameter today what do we call it? You heard the name. I know you heard the name. No brave student? How do we call Hubble's parameter today? Maybe you're all muted then.
I thought about cosmological constant, but it's constant. It cannot change in time, right?
It's called Hubble's constant. Not cosmological. We'll get to cosmological constant. It's not a cosmological constant. It's simply called Hubble's constant. And as you can imagine, there is nothing constant in this constant. It's just the name. Today is called Hubble's constant. And it's denoted with a 0. In general, in cosmology, when we want to refer to something that happens today, we put a 0. So 0 is today. And it all goes backward in time. So something which is far in the past. We'll get to rate. It's called H0. And it is defined as A dot over A at T, which is equal to T0. Now it is approximately 70 plus minus 3 kilometers per second per megaparsec. So megaparsec, if you don't know, this is a quantitative unit of distance to other galaxies, and it's a megaparsec is 3 times 10 to the 24 centimeters. Now, in fact, the most accurate measure that I have is from 2018. That's the last one I know, but I don't think there was anything which is new. That is called H naught from the Planck measurement is 67.66 plus minus 0.42 kilometers per second per megaparsec. That is from a Planck satellite. Now, you might have heard, I don't know if you've heard it, about what's called the Hubble's constant discrepancy. Did you hear about that? This is something which is very new. There is more than one way of measuring the Hubble's constant. We can discuss that. There is one way which is related to the nearby universe, and there is one which is related to the very old universe, just after the Big Bang. Now we have not, I'm a little bit jumping because we have not discussed about the Big Bang and what can we measure from there. And there seems to be that these two numbers are misaligned to a 5 sigma level. And that causes a trouble. Obviously, Hubble's constant, again, not to get confused, it is not a constant, it's changing in time, but it is measured in today. And you know, before I jump into telling you the stories from the latest debate that happens among cosmologists about what is the true value of Hubble's constant, let us see for a second why this is so important. Why do people spend so much time on measuring the Hubble's constant? So I'm going back to the second of Friedmann's equation, which is written here. A dot over A squared is equal 8 pi G over 3 rho minus K over A squared. And I can write this if I'm using the Hubble's parameter, right? A dot over A squared is just H squared. So I can simply write this as second Friedmann equation. I can write it as 1 is equal 8 pi g over 3h squared rho minus k over a squared h squared. Yeah, let's see it from here. Okay. Now we can define the critical density. Remember, it's an energy density. So rho critical is 3h squared over 8 pi g. And currently at present day, so rho critical 0, that is today. Remember, every time I put 0 into something, that means today. This is equal to 3h0 squared divided by 8 pi g. So essentially what I need is to measure the Hubble's constant. Right? G is a constant, we know what it is, the rest are constants. This is equal, if you want the numbers, it's 9.21 times 10 to the minus 30 grams per centimeter cube. Or physicists like to work in electron volt, so it's 5.19 times 10 to the 3 electron volt per centimeter cube. And we can further, to simplify this equation, we can define what is called as the density parameter. Which is denoted by omega. Kosmology is also something that people like. So there is omega, omega matter, omega photons, omega dark matter. We get to that. This is defined as 8 pi g over 3h squared times rho, simply rho over rho critical. This is the definition of the density parameter. How comes the punchline? Using this density parameter, I can take this second of Friedmann's equation and I can write it as what? Omega minus 1. I'm just shifting that over here. Is just k over a squared, h squared. This is the same Friedmann's equation. Yeah? Now you see the trick? So, if rho, energy density in the universe, is smaller than rho critical, what does it mean? About omega?
K is
Smaller than
minus 1.
Omega is more than 1.
Yeah.
If
And
omega
our
is,
universe has negative curvature.
omega is more than 1, then automatically we must have that k is more than 1. Means that our universe has to be k is less than 1.
There are two cases, right? 0 or minus 1.
There are 3 cases for k. How do we call a universe with k which is smaller than 1?
We had 3 cases. K
Yes.
equals +1, 0, or -1, right?
Correct. How do we call a universe with a k which is -1?
So negative curvature, right?
Open.
Yes, open.
So if rho is equal to rho critical, then what does it mean? That
Omega is exactly 1 and k is 0.
k has then to be 0, which means that the universe has to be
Flat.
Flat.
Of course, if rho is greater than rho critical, then omega needs to be greater than 1, in which case, say, it's actually, I wrote it's more than 1, but we said there are really 3 options, so it's not more than 1. K is simply equal to -1, and here k is equal to +1, which means that the universe is closed. Now, rho is the energy density, something which in principle we can measure. If we can look at everything that there is in the universe. Rho critical, again, it's defined here, is something which we measure if we measure the Hubble's constant. Right? Rest are parameters. Right? These are things we can measure basically. So we have a way, in principle, of telling us whether the universe is open, flat, or closed, or what is the value of k up to this, +1, -1, or 0. Does any of you happen to know what is the measured value of omega?
I guess it's close to 1. And the universe is flat.
So the answer is yes. It can be anything from what we have.
Not too good to be perfect.
What?
It's not too good to be real. Like if
Yes.
there is no reason that the space is flat.
Absolutely, you're right. In the theory, as is being derived, there is nothing that tells us what the value of k should be, what the value of omega should be. Right? Remember, we're measuring the Hubble's constant, and we're measuring the sources of energy in the universe. So, what do you mean by sources of energy in the universe? So we have matter, as we know it, stars, galaxies. We have what we call relativistic matter or photons. So we know what is the energy density of photons in the universe. That's how we measure rho. And we measure the Hubble's constant, which essentially tells us how the universe accelerates. Essentially, there are various ways of measuring it, which is, well, initially what Hubble was doing, actually I didn't bring it here, but okay, it's very easy to Google it, right? Eventually what Hubble was doing is measuring distant galaxies. He was measuring the distance to the galaxy he found a way of measuring the distant galaxies using variable stars, and the Doppler shift saying how much the galaxies recede away from us. We will discuss that. We'll discuss Hubble's law. This will be likely next week, or maybe this. I told you we don't want to miss the last parts of the last courses of the semester, because that's where we're going to talk about the really fun story, the really fun part. So yeah, so we'll discuss Hubble's law and how we did these measurements. So these are all measurements, right? It's all something which we can measure in the what we call today the nearby universe. We don't need to go too far today. There are other methods. The technology is obviously advanced since Hubble's time, and we can measure various things, which we'll discuss later. And at the end of the day, we could have gotten any value. We could have gotten 27 for omega, right? Could have gotten 0.05. But no, we got to 1, up to errors. And the errors are such that they allow any universe. And yes, this sounds like some sort of a conspiracy. I agree. I mean, there's nothing that tells us why it should be like that. And that is one of the starting points of a theory which is called inflation, which you might have heard the name of, which is there to explain various of these observational results, which seems to be conspiratory, which seems to be coming out of the blue. So even if the universe is not flat, it's very close to flat. So it's so close that the idea is that there might have been some driving force that caused it to be very close to flat in the beginning. And that's the idea of inflation is there to solve that. It's also there to solve some other problems, such as why the galaxies are isotropically distributed, although they had no time to communicate with each other since the Big Bang. But I'm going slightly ahead of time, because we did not yet speak about the Big Bang. So this, I think, we'll have to wait until the next lecture on Thursday. All right. Any further questions about that? Just say why.
Can the curvature of the universe also evolve with time? Because I see definition of the density parameter, and it's rho divided by rho critical. We know that rho is energy density, right? So
Yes.
it's how energy
Evolving.
yeah. So the energy is the universe is expanding, but there is no any new matter, right? In our
We're going to
universe.
discuss that. We'll discuss that on Thursday. So yes, we'll discuss the evolution of the universe. Say starting point of inflation. I will only mention that all these measurements are done today, so they don't rely on what happened in the past. What happened in the past is something which we deduce. But the measurements I'm talking about are things that are done today. When I say today, we distinguish between the what's called nearby universe. Galaxies in our own neighborhood, and the very far universe. And indeed, of course, because it takes light time to travel from the galaxy to us, nearby universe basically means that the light, the universe did not change much from the time the photons were emitted from these galaxies until we see them today. And the old universe means that the universe have changed a lot from the time the light was emitted until we see them. That's called a redshift, cosmological redshift. And again, we will discuss that, I promise you. We won't finish the semester before discussing that. We still have, I think, 3 more lectures, and they will cover all of these subjects. So don't worry about it. Just if you come to the lectures, it will be there. Okay, I think it is a reasonable place to stop. The answer is nobody knows why it is so. And we still don't know whether the universe is open, flat, or closed. It can be the best measurements we have today allow all 3 options. And yes, it's true that even if it's closed or open, not flat, it's very close to being flat. And theory of inflation is there to explain why it is so close to be flat. Whether it's correct or not, I don't know. I'm not convinced. I'm not an expert in this theory. Okay. Any further questions? Any further questions, guys? No. Okay, so I think it's a good place to stop here, and we'll resume the discussion on Thursday. I wish you all a quiet week. One last thing, I was asked for an extension in homework, so yes, you can get the extension. I don't have any problem with that. But I don't recommend it. You know, it's a stressful time. I guess you're being stressed from every place, and we're getting quite close to the end of the semester and the end of you know, the examination period. Of course, I've got no idea how it's going to work. I think nobody has an idea. Yesterday evening, we got a notification that we can go back to offices, and to this morning at 7 a.m. there was notification that because of the recent developments, then we still not allowed to go to offices. Those things, as you know, I don't need to tell you, evolve by the hour. Stay safe, and I will give you this week one last problem set, and I really view it for you guys. I mean, I really view it as something which is, you know, for you to practice and understand what we're talking about, so that you don't get, how to say, you know, that you understand what we're saying here. I think, I know, I hope this is you know, the fun part of the course. I hope you really enjoy it. I mean, the most fun part of the course. I think this whole course is fun, but then it's up to you to decide. All right, guys. So
Thank you.
Thank you.
have a quiet rest of the week. And if you have any questions or any problems or anything, just drop me a line. And I'll see you all on Thursday. All right.
Thank you.
Thank you, guys. Bye-bye.
Bye.